Hello, everyone. My name is Jawad Orbani. I'm a research fellow at the Department of Civil Engineering, and the topic of this presentation is AI QA, where practitioners inside with algorithms, better roads and fewer repairs. Roads are the circulatory system of the economy. They move people to work, goods to market, and service the communities. And when road quality slips, the impact isn't just rough rides. It shows up as real recurring costs to households, businesses, and governments. In Australia, the estimated social cost of road crashes is about 27 billion per year, a burden carried across families, workplaces, hospitals, insurers, and public budgets. And this is clearly a global problem. In the United States, for instance, 39% of major roads are rated poor or mediocre, and deteriorated conditions cost the average driver around $1,400 every year through extra vehicle wear, maintenance, and time lost in congestion. This becomes even more challenging in developing countries where budgets and equipments are tighter, and the same construction defects can shorten road life much faster. It's also interesting to know that based on a Federal Highway Association report, $1 spent on timely pavement prevention can avoid and delay $6 to $10 in future rehab reconstruction costs. Even though we know good quality assurance and quality control prevents a lot of road damages, the real question is why it is still so difficult to do consistently. It's important to note that roads are built on naturally variable materials. Unlike steel or concrete, soils are not manufactured to a uniform standard. Their properties can change over very short distances, even within the same project footprint. The most critical layers are the least visible ones. Pavement performance is strongly influenced by the subgrade and base layers, where moisture condition and compaction quality are decisive. If either is slightly off, the problem gets sealed beneath the asphalt and only become obvious as rotting, cracking, and potholes. And this is why using pure advanced analytics or AI-driven model is generally harder in roads than any other fields in civil engineering. Even with very strong analytics or AI models, the data feeding them is often sparse and uncertain. This slide highlights the core challenges in application of advanced analytics to improve quality assurance and quality control of road construction. Performance of these models generally depend on many interacting ground and construction variables, but we rarely observe enough of them during road construction. To make reliable predictions, we need strong models and high-quality, sufficiently dense data. In practice, that data is often missing. As this image suggests, field devices may measure only one key variable, such as density, but other critical drivers like moisture condition, soil variability, underlying layer conditions are all unmeasured or only sampled occasionally. When these inputs are missing, models are forced to assume or use rough proxies, and those assumptions introduce uncertainty and reduce accuracy, especially because small errors in moisture or subgrade condition can dominate long-term performance. Finally, sparse data make it difficult to create a strong feedback mechanism, which is essential for optimizing AI models. Now, how do we address these problems? The way we did that was through augmented intelligence. What we realized was that practitioners were working with the compaction equipments and are present on site usually carry an invaluable intuition which is built over years of experience. In many cases, they can judge compaction quality and ground behavior quickly, even based on cues like material responses, roller behavior, surface movements, and how the layer sounds or works on their equipment. What surprised us was this valuable expertise is rarely captured or used systematically in real time. It lives in people's head, gets applied informally on site, and is often lost between shifts, crews, or projects, exactly when data is sparse and uncertainty is highest. Then our biggest challenge then was to bring that intuition somehow into the AI model that we had in a way that it is machine readable, it's human understandable, and it can also strengthen the entire QA pipeline by improving data coverage, building more reliable models eventually under uncertainty, and enriching the feedback loop that we have. So the technical details and results are available in a recently published paper, collaboration with Monash, University of California, San Diego, and the University of Melbourne researchers. And we are currently awaiting a decision on a second manuscript on a closely related topic. I won't go deep into methodology here since it's covered well in the paper, but in brief, what we did was we combined unsaturated soil dynamics, which is essential for understanding the behavior of soil during construction, and it forms the core physical knowledge of the system, with fuzzy logic, which basically interprets human inputs or practitioners' input to handle uncertainty, and then use local and global optimization using particle swarm optimization for calibration, and supported the entire workflow with machine learning surrogate model to speed up simulation and the analysis. And in terms of application in the field, so far we could basically test the model both indoor and outdoor. Some example pictures are shown. And these tests basically helped us to optimize some of the assumptions that we had initially about the model performance, and eventually we could reach a stage that we are today. And in terms of RACE and EIP support, I would like to mention that the analytics that we used required running many simulations and training machine learning models iteratively. This could not be done in personal computers. And then RACE made this feasible by providing a scalable cloud compute accesses, an accessible platform for our simulations. And I acknowledge their support. Also, the team offered technical consultation on developing the graphic user interface for the software we developed. And event like this, of course, create a structured space to share the work, get feedbacks, and shape next steps toward the impacts. And in terms of project progress so far and future plan, I would like to mention that the graphic user interface was developed. The prototype is complete now, and core workflow and user interactions have been implemented and validated internally. And we're preparing the next phase of industry engagement to validate the code and run pilot use cases and refine the product for real site conditions. And here we believe that EIP network can provide invaluable support, and we are looking forward to that. And in terms of scaling, I think the key plan is to extend this code beyond the initial scope by integrating additional testing equipment, common testing, geotechnical engineering, construction, quality assurance. And of course, when you consider that, you need much more computing power, and that's where we believe that RAISE support would be invaluable, and we are looking forward to that one as well. And thank you so much.